Great. All right. So welcome everyone to day 3. And so today we're going to be covering lithospheric deformation. This is going to be presented by myself and Anne. And rather than start from where we left off yesterday, I think what we're going to do actually is cover some of the material we briefly went over at the end of yesterday, just so there's no confusion about things like viscoelasticity and such. So I will quickly share my screen and then we'll jump right into the presentation. There it is. Can everyone see this okay? Excellent. Right, so today, as I said, we're going to be covering lithospheric deformation, and I slightly reordered things from yesterday. So yesterday, what we actually did is we went through the basics of viscoelasticity and then jumped immediately into this bending beam example. What I thought would be useful to start with today is do an overview of both viscoelasticity, nonlinear viscous flow, and plasticity. So effectively do an overview of all the relevant equations and numerical methods. And then we'll go systematically into each example. So what I'm actually going to do is start by running the bending beam example benchmark. And what I'm going to have people do is first you can look at the screen and enter the commands based on this, but then I'll go into my virtual machine and do the same thing unless there's any confusion, in case there's any confusion. So the first thing what you can do is if your virtual machine is running, please CD, open a terminal, and then CD into the aspect tutorials as we've done the last 2 days. So the command would be cd /aspect tutorials /2020 tectonics modeling tutorials /session-3. And while I'll leave that up for maybe just 10 more seconds, and then once that's done, I will go back to my virtual machine so everyone can take a look there. All right, and I will see if I can open my VM now. Great. Can everyone see the virtual machine okay? Renee, can you give me a thumbs up if you can see the virtual machine? Thank you. Great. So, yes. So right now we're in the virtual machine, and we're in the terminal, and we're in the aspect tutorials 2020 tectonics modeling tutorial -session-3. And if you do ls, which is going to show everything in the folder, is you're going to see all of today's examples. So we have the brittle thrust wedge, continental extension, prescribed subduction, and viscoelastic bending beam. And what we want to actually start doing is running the viscoelastic beam benchmark. But the first thing to do is actually open it and change a few parameters. So if you type leafpad or xdg-open, viscoelastic bending beam. Oops. Sorry. Apparently I'm overloading my computer with applications right now. So once you have this open, if you can scroll down to past all the documentation, and we will go down to a section which says, or the parameter which says set end time. And I will see if I can quickly increase the size of this window. Sorry, I'm a bit hesitant to go to full screen on this virtual machine. The last time I did that, my keyboard froze, so I'm not going to go that route. So, but basically what we can see here is the model end time is set to 10,000 years. And if you're running in debug mode, or if your computer was not running models quickly the last few days, you should keep that value at 10,000 years. If, however, you're running in release mode, or you can use, let's say, 4 processors, please go ahead and change this to 50,000 years. Yesterday, I was able to run this in 20 minutes on release mode at 50,000 years. But if it's at 10,000 years, it'll running in debug mode on say 2 processors, it'll likely take maybe an hour or so. So if you're running in debug mode, oh, sorry. Yeah. And so if you're running in debug mode, please keep it at 10,000 years. But if you're running in release mode, please go ahead and change this to 50,000 years. So once you've done that, please close it, and then we can start running the model. And the command for this, at least if you're running in release mode, would be tilde aspect /aspect -release, or whatever you named the value of the release executable. If you're just running in debug mode, aspect release would just be changed to aspect. And then, oh, sorry, and then I forgot to add there, at the beginning of this, you would need to have MPI run -np2 is what I will use. And then the name of the aspect executable. Or no, I'm sorry, the name of the parameter file. Yep. And so that's running now. And what I'll do now is go back to the presentation, and we'll let that model run while we go through the viscoelasticity section again. Great. So, did anyone, I'll leave this up for another second in case anyone was not able to follow along the virtual machine. Are there any questions about this before I move on? And please go ahead and ask them in the chat.
There is a question in the chat, John.
Okay. Renee or Lorraine, would you actually be able to read that? I can't access the chat.
Sure. So is it necessary to run this with 50E3, or is it better if someone has already run it with 10E3 to just leave it at that and not try again?
It's fine. It's fine to leave it at 10E3.
Okay.
The lessons will still be the same. Great. So a few introductory notes, which we covered yesterday, but I wanted to go over again. So today we're covering lithospheric deformation, and the first note is that just keep in mind there are a huge number of contributors to this part of the code and all the benchmarks and examples. So it's not just Ann and I. There's probably well over 30 to 40 people who contributed to code and examples associated with this content. The second point is that this really is meant as an introduction and not a comprehensive overview. The next step, if you're new to lithospheric dynamics, is to then review all the additional examples and aspects, the cookbooks and benchmarks, the aspect source code, the aspect manual, and then after that, start going into the literature. So this really is just an introduction to sort of give you a sense of how these things work. And then probably the most important point here is this is a really difficult topic. And you really need to properly set your expectations for the time required to do modeling in a novel study. If you're, and this is particularly true if you're new to it, there are a lot of people here who have quite a bit of experience in this field already, but if you're new to lithospheric dynamics modeling, then expect to spend a year probably just sort of getting a sense of how these things work before you can actually start, sort of conducting a serious study, especially if it involves implementing new physics or running large 3D simulations. So I thought the next thing that would be useful to do, and Wolfgang and Timo sort of covered this a bit on the first day, is to go over numerical modeling from start to finish, and then how it relates to how we set up a lithospheric dynamics models. So the steps would be as follows. First, define what physical processes you want to examine. Then you would try to capture the physics of these physical processes through equations. After that, you would choose a numerical approximation to solve the equations. In this case, we're using the finite element method. Other people use the finite difference method or spectral element method. After that, you would design, write, and validate your software package. In this case, you can maybe just take a step of validating the existing code like aspect or something else. After that, you would formulate a very detailed hypothesis to test. Then based on that hypothesis, design and run a series of models. and then finally verify and interpret your results. Now, the main thing to take out of this, if anything, is that you've already moved to step 4, right? And so then there's already existing code, and it's actually well validated. We spend quite a bit of time testing and making sure everything is working properly inside the code. And that's a huge advantage, right? So, so basically you don't need to go through steps 2 through 4, but under no circumstances should you skip steps 1 and 5. And I'm saying that for this reason. While Aspect has a lot of physics implemented within it, and you can do a wide variety of problems, it's not all encompassing yet. So there's still a lot of things we as the development team and others want to implement in the code. And so then before you start on a problem, the first question to ask yourself is for the specific I want to model, for the specific problem I want to model, does Aspect actually contain the relevant physics? And the answer may be no. And so then you may need to do some coding initially to implement those physics. And then after that, in order to have a successful modeling study, you really need to start with a very specific hypothesis test. And the reason for that is this. There's so many parameters which go into lithospheric dynamic models that you simply can't vary them all. And so you can't say, I want to model subduction. Well, there's thousands of potential combinations of parameters, that control subduction. And so then what you have to do is think carefully about what aspect of, say, the subduction system I want to test. Do I want to test the effect of the initial, sort of oceanic plate age? Do I want to test the effect of subduction velocity? Do I want to test the effect of the overriding plate strength or the plate boundary strength? And so then until you've done that step, it's really hard to design a useful series of models unless you have a very specific hypothesis you're going to test. So always start with steps 1 and 5. So what are the physical processes associated with tectonic modeling or long-term tectonic modeling? It's sort of, we use this phrase long-term tectonics for thinking about things like subduction, continental breaking, mid-ocean ridge spreading. But actually, what we're going to be talking about is processes which we're just be covering tectonics. And so it could fall in the range of short-term tectonics all the way up to long-term tectonics. But for tectonic processes in general, what we're effectively talking about is crustal deformation, lithospheric deformation, and mantle convection. And the important part about that, since we're covering all these very distinct parts of the Earth and the physical processes associated with them, is that the relevant temporal and spatial scales and the associated deformation mechanisms are quite different across all those different things. And so then if you think about the smallest time scales you can model, that's actually grain size evolution. And so the deformation of grains in response, in response to plate driving forces. And that's occurring at scales of less than, on the order of a second or less, and, on the order of millimeters. If you go all the way up to mantle convection, suddenly you're talking about modeling processes over billions of years and scales of thousands of kilometers. And so then for lithospheric deformation and tectonic modeling, we're actually covering basically everything in here. And so in some of the models people start developing Aspect, they're actually specifically looking at earthquakes and faulting. I say the majority of tectonic models sort of fall in this range in terms of crustal deformation and lithospheric deformation, then also in some cases, two-phase flow and magma transport. And so these are sort of on scales of like tens of meters to hundreds of meters, all the way up to hundreds of kilometers, and temporal scales from years to thousands of years. But still, even within that range, this is really tricky, and there's a whole bunch of different deformation mechanisms which fall within this range. And so then all that needs to be taken into account when designing the model and thinking about what problem you're setting up. So before we even get into the rheology section of lithospheric sort of deformation, let's actually go back through some very, the most elemental equations as it relates to mantle convection and Aspect in general. So then what this is showing right here is the governing equations for incompressible viscous flow. Of course, Aspect can do much more complicated scenarios where there's compressibility, but oftentimes in lithospheric dynamic codes, at least up until now, most people use some sort of incompressible viscous flow formulation. So something like the Boussinesq approximation. So then how are these equations written? So you can kind of divide this up into the Stokes equation and the conservation of energy. This equation right here would be conservation of mass, and then where U is velocity. This would be the force balance equation, where sigma is the stress tensor, P is pressure, rho is density, and G is gravity. So then this is sort of describing independent of temperature or anything else, how the forces balance and how mass is conserved throughout the system. When you solve this equation, it's time independent. So then it's a single time step. And so then you have your buoyancy forces, you have all these terms, and it's basically an instantaneous solution. The time dependent component starts to come into play when you think about conservation of energy. So here we're thinking about advection and conduction of temperature. So then here rho is density again, C is the heat capacity, T is temperature, or small t is time, U is velocity, again, T is temperature, K is thermal conductivity, and H in this case is something like internal heating. And then of course, you can have a much more complicated version of this equation if you have things like adiabatic and shear heating and other terms related to compressibility. So then moving on to the rheology, and this is really sort of the heart of the tectonic modeling component is then, so then how do you describe the material deformation in tectonic plates and the uppermost mantle? Well, we saw part of this yesterday, and that I'm certainly going to break this down into 3 different parts. 1, viscoelasticity, 2, nonlinear viscous flow, and then 3, plasticity. So the way viscoelasticity works is that you basically modify a viscosity, an initial viscosity, calculate stresses associated with viscoelasticity, and then add those onto the force balance equation. So then here, this term is the viscoelastic viscosity, and this is equal to sort of a background viscosity, times an elastic time step component divided by this elastic time step component plus the background of viscosity divided by the shear modulus. The shear modulus is an elastic constant. And of course, this is also assuming incompressible elasticity. We're not gonna, we haven't implemented or even begun to design how the code would look if we had compressible elasticity. It's a much more difficult problem. And of course, if you had compressible elasticity, then you would also need to think about the bulk modulus. But here we're just thinking about the shear modulus. One thing to note is this background viscosity we're modifying here. In aspect, the order of operations would actually be you calculate the viscosity from, say, diffusion or dislocation creep or some composite thereof first. So then we actually are sort of, I'm actually doing things a bit out of order here, but that's okay. It's not that big a deal. But just keep in mind, this is from diffusion, dislocation creep, and basically step 2 in the series of, or at least in the numerical procedure, is to calculate this viscoelastic viscosity. Then after that, you would calculate the stresses associated with basically that viscoelastic viscosity and the rates of deformation in the model. And so then the terms here are the viscoelastic effective viscosity, you have the strain rate, you have the viscoelastic stress from the previous time step. Again, you have this elastic time scale, the shear modulus. This is basically the vorticity tensor. Here are the stresses again, and you have the shear modulus. The overall, how this equation is designed, it doesn't matter so much for the purposes of this tutorial. I just wanted you to get a sense of the terms that are in there. But so then once you have this stress term, what you can do is say, I'm going to calculate a viscoelastic force associated with the stresses. And so this force value is equal to the negative 1 times the viscoelastic viscosity divided by the shear modulus times the elastic time step times the stress tensor. And then this term basically gets added onto the force balance equation. So 2 things are happening here. One is you have basically a reduction in the viscosity associated with viscoelasticity, but then that is counteracted by adding these additional stress terms onto the force balance equations. And then this procedure, it follows the approach of Louis Murasi in his code Underworld. He wrote like his original formulation for this was written in this paper in 2003, and this is hyperlinked, or at least this text right here is a hyperlink, and it'll take you straight to a free version of the paper. And for the most part, although there are some deviations, basically all of the lithospheric dynamic community largely follows this approach, with some variations. So, how about nonlinear viscous flow? So diffusion, dislocation creep, and then plasticity. So then what you might do in a lithospheric dynamics model is first calculate a temperature, pressure, and strain rate dependent viscosity associated with nonlinear viscous flow. And so what we're saying here is the stress associated with viscous flow is going to be this pre-exponent raised to the -1 over power n. This right here is the strain rate or the dV torque strain rate invariant. Again, this exponent n pops up again. These terms are related to grain size, and then here E is the activation energy, P is pressure, V is the activation volume of n again, and then the gas constant times T. And then you can also rewrite this equation to formulate directly in terms of viscosity. Now, an important point to note here is that there's basically, this equation could be divided into a couple parts. If you have diffusion creep, n is equal to 1, and then grain size also plays a role. If you have dislocation creep, n is greater than 1, and grain size does not play a role. So often, so what we actually do in Aspect is we separately calculate diffusion and dislocation creep viscosities, and then after that, what you can do decide is to use one, one or the other, or have some composite of them, and so some average between them. In the material model we're going to use today, we basically, when we do a composite, is we do a very simple averaging between these two values. This is actually not the ideal way to do this, and there's a different material model and Aspect which actually does a local iteration to figure out the proper stress, basically partitioning between diffusion and dislocation creep. That's going to, at some point this year, next year, that's going to get ported over to the material model we're going to use today as well. Then after that, you would, after you calculate the viscosity associated with nonlinear viscous flow, is you would do the viscoelasticity step we just went over. And so you calculate an effective viscoelastic viscosity, calculate the force associated with the stresses, the viscoelastic stresses, and then add that to the force balance equations. And then the final step would be to model plasticity. And so what effectively plasticity is, it's our approximation for brittle failure. And so what we say is we might use something like a Drucker-Prager-Rheology criterion. So we say the stress limit associated with brittle failure is going to be equal to the pressure times the sine of the friction angle plus the cohesion times the cosine of the friction angle. And so then the procedure there is to say, okay, are the stresses associated with nonlinear viscous flow and potentially viscoelasticity, if you included, are they greater than this value here? If they are greater, then we're going to calculate a new viscosity, a plastic viscosity, which lies directly on that yield plane. And so we basically divide the stress by the strain rate, and then that's going to give us a new viscosity. Now, one thing to note is you can actually make this procedure a lot more complicated, and that what we're going to have one example or multiple examples of today is cases where the friction angle and the cohesion actually depend on the accumulation of finite strain. So what you can do is over time, you can track areas which are undergoing brittle failure and actually say, okay, we're going to accumulate plastic strain over time, and then the friction angle and cohesion are going to weaken linearly as a function of those things. That helps localize deformation over time, or even initially as well. So some additional notes on rheology before we start going into the bending beam example. These nonlinear systems of equations we just showed on the previous page, they are not trivial to solve. They require both global nonlinear iterations, and we'll go into a bit of what exactly that means, and in some cases, local nonlinear iterations to solve. And so both you're doing these global iterations to adjust, to look at the dependence of temperature and strain rate. But in some cases, this is not implemented in Aspect, but some people also do local nonlinear iterations. I guess one example of that would be the partitioning between deformation mechanisms, forward diffusion and dislocation creep locally. So then this is really hard, and a lot of things can go wrong when you're doing these nonlinear iterations or designing your model, which will give you very bad convergence behavior. And that leads into the second point, where then as you design your models, frequently what you see happening is, depending on the features you put in the model, your boundary conditions, your initial conditions, basically anything, changing certain things can lead to a significant change in the number of nonlinear iterations required to solve the problem each time step. And so then, while in 2D, that's not such a big deal if you're saying doing 50 to 100 nonlinear iterations per time step. If you're designing a large, highly time-dependent 3D simulation, which needs to run for millions of years, doing 50 to 100 nonlinear iterations per time step is simply not practical. It means instead of being able to run 10 models for your study, you're going to be able to run one model, or something like half a model at the normal time you would normally run it. So then when you're designing your models, actually quite a bit of time, or at least I spend quite a bit of time, designing setups which exhibit reasonable convergence behavior. And that's actually a real challenge when you're doing 3D simulations. Some notes, of course, a lot of this is described in the manual and the various material models and other parts of the source code. But if you want to get a sense for especially how plasticity and then the nonlinear viscous flow work, I would recommend reading these 3 papers. There is not a paper yet for the viscoelasticity, but a number of us are working on that, and that'll likely be coming out sometime early next year. So if we go back to the 7 steps we were discussing, the next step would be, how do you formulate a hypothesis to test? So then we have a working code. And now what we want to do is actually think about designing a model based on a specific problem or observation or inferred process. And so then in designing this, you want to test an idea which you can actually solve with the code you have. And so then things you often see in the literature or problems being addressed are things like, how does the rheology affect deformation patterns? How does the rate of deformation and affect observed deformation patterns? Or something like, how does the initial lithospheric structure? So you can think about structural inheritance. How does that affect the long-term deformation patterns? These are questions you can address with, with this type of code. And so what we're going to do for the rest of today and part of tomorrow is look at a few examples of this. We're going to look at a case for continental extension. We're going to look at a case for subduction. We're going to look at a case for thrust sheets. And in the first case, we're going to go back to this bending beam example where it's actually sort of mimics what's happening at the hinge of subduction zones. So again, quickly to go through viscoelasticity, why is this important? And when viscoelasticity, or at least these effects, are quite important in regions undergoing flexures. So this could be an example at Hawaii, like at an island chain where you have significant growth of volcanoes, and this is causing the lithosphere to flex. Here you have significant viscoelastic forces accruing, and then it would also be the case at subduction zones, where you have bending of a cold oceanic plate, and then that should lead to a large accumulation of viscoelastic stresses. Viscoelasticity, of course, is also important at very different scales. You can think about elastic deformation in the interseismic cycle of earthquakes, and then also even longer-term deformation. Viscoelasticity can play an important role in the evolution of normal faults. But at first order, it's extremely important in regions undergoing significant flexure. So in terms of viscoelasticity aspect, there are actually a bunch of examples of which you can build off of if you want to include this in your models. The material models, there's a specific material model called viscoelastic, which is designed only to simulate very simple viscoelastic problems, but then you can also simulate viscoelasticity in the viscoplastic material model. But then in terms of how the code is structured, actually what these 2 material models are actually calling is there's a separate module which contains most of the code associated with elasticity, and that's called the elasticity rheology module. In terms of available benchmarks, there's a very large number. Today we're going to be looking at the viscoelastic bending beam, but there's also another one of viscoelastic, one called viscoelastic beam modified, which has an open top, which has open boundary conditions and does a bit better job at modeling certain flexural profiles. There's a case where you have accumulation of viscoelastic stresses under constant strain rate. There's a case where there's a free surface and you look at viscoelastic deformation of a plate in response to basically a buoyancy force on one side. There's a case, which is actually a really useful one, where then you have a free surface, but then you actually apply a variable load on top of that free surface and look at the deformation over time. That's basically mimicking something like sort of ice sheet loading over time, or something like growth of like an oceanic Hawaiian chain, like Hawaii or something like that. And then we also have some cases where we combine viscoelasticity with plasticity. We're not going to talk about these cases today, but these examples are there if you'd like to take a look at them and try implementing this in your model. There's one called viscoelastic plastic shear bands, and then plastic simple shear. One of the reasons we're not going over that today, and why we haven't sort of published some papers on this yet, is the nonlinear convergence behavior, or so far, it drastically worsens when we include elasticity, and we're basically working on solutions for that right now. So again, there's no paper yet, but there is lots of documentation within aspect and within these examples. So now what you can do, this is optional, if you want to go back to your virtual machine and then open the viscoelastic beam benchmark. I'm not going to go back to the virtual machine. I'm just going to go through the sections of this, and I've included these, on the, I've included the main or the key components of the parameter file in the slides itself. But if you would like to follow along directly, please go back to the virtual machine and you can scroll through that parameter file as you're doing it. So the viscoelastic bending beam benchmark, again, this is designed to basically look at the flexural profile and viscoelastic stress accumulation of a viscoelastic plate under gravitational loading. So here's the model design. It's 7.5 by 5 kilometers. We have 100-meter grid spacing. And here are the key features and boundary conditions of the model. On this side, it's no slip, meaning the velocity in the X and Y component is, of course, set to 0. On the top and bottom and right, it's free slip. And so then along here, you can have horizontal flow, but no vertical flow. And then across here, there's no material moving in or out, but it's unconstrained in this direction. You have gravitational loading, and the value of gravity is 10. And what you have then is you have two different materials. One, you have a viscoelastic dense beam. And so then basically it has a higher viscosity than the surrounding fluid. It has a higher density, and it has a lower shear modulus. And so what that means is that if you turn on gravity, what's going to happen is this beam is going to start to bend. And then as it bends, viscoelastic stresses are going to accumulate. So again, this is the video we saw yesterday. This is the beam bending over time. The red represents a compositional field. And so then what happens is we're using this compositional field to track the different materials over time. But of course, these methods are not perfect. And so what you do see is some diffusion. So at here, the value is 1. Here, the value is 0 of this compositional field, but it's sort of at the edges, you do get some diffusion over time. And so then similarly, after 50,000 years of deformation, what you're going to see is that you've accumulated on the order of 200 megapascals, up to 200 megapascals, 200 megapascal of stresses. And of course, the values, depending on what side of the beam you're on, at the top, it's undergoing tension, at the bottom would be undergoing compression. These values are going to be polar opposites. And again, right here, what you end up seeing is because of the advection, some issues with the advection of the compositional field, you sometimes do get these stress anomalies right there. But it turns out they actually, in this case, they don't really affect the accuracy of the solution that much at all. So then if you look at in the parameter file, how you actually design this model, it's actually pretty straightforward. And so then if you look at the global parameters, so here we set the end time to 10,000 years, at least in the example in the virtual machine. A number of you may have changed that to 50,000 years. The CFL number is set to 0.5, and I can't remember if we covered the CFL number on the first day, but basically what that does is it limits the time step. The CFL condition, it's basically a function of the mesh size and the velocity. So based on those two parameters and the value you give it here, it's limiting the size of your time step. Because of course, if your time step is too large, your solution for the advection is going to be inaccurate. So then this is a pretty standard value of this CFL number to use. Often if you're doing models with plasticity, oftentimes I reduce this value to 0.1 or 0.2. But here we're actually doing a bit of a trick. Is for the purposes of simplicity and looking at stress accumulation over time in a systematic fashion, I've actually set the maximum time step equal to 1,000 years. So it doesn't matter what time step is determined by the CFL number right here. If that value is greater than 1,000 years, the time step is always going to be capped at 1,000 years. And in this case, the CFL condition always gives a value larger than 1,000 years. And so we have a constant time step each time. In terms of the driving forces, and so then this is the gravity section of the material model. And so then what we're doing is because we're working in a 2D box, or it wouldn't matter if even a 3D box, is the name of the model we're using for gravity is vertical, so it's pointing straight down, and then we set the magnitude equal to 10. Another really useful feature here is we're doing checkpointing, which allows you to restart your model after it starts. And so then in the global parameters, you actually have a parameter called set resume computation equals auto. And what that does is if you restart your model, this automatically detects if you're writing out these checkpoint files. And so then at the bottom of the parameter file, we have the section called, or the checkpoint subsection. And what it says is we're writing out these checkpoint files every 10 years. And so then in terms of the time step, that means every 10,000 years, we write out a checkpoint file, which allows aspect to restart from that point. And so let's say you ran the model for 50,000 years. What you would have is you should have a checkpoint file exactly written out at 50,000 years as well. And if you restart the model, then it'll just continue on. And to have the model continue, all you would need to do then is change the end time to something larger than the original value. So the number and name of compositional fields. And so then what we do is we actually need to track four different compositional fields. We're going to have 3 compositional fields for the stress tensor, and of course in 2D. And of course in 2D, you can approximate the stress tensor with just 3 components. So we have horizontal stress, the vertical stress, and then the shear stress. Now, you actually were very specific about how this needs to be done. And if you're using viscoelasticity in your model, if you have viscoelasticity turned on, you actually need to list these fields first. And if you don't list these fields first in this exact order, it's going to, aspect is actually going to kill the model and throw an error message. And this error message is going to say, if using viscoelasticity in 2D, these 3 compositional field names associated with the viscoelastic stress tensor need to be listed first. So, and then the last one is the viscoelastic bending beam. And so then this describes, like the actual beam, which is being bending. And then the material surrounding the beam is basically the background field. And so then we could have added a compositional field to track it, but the way aspect works in terms of looking at different lithologies, we actually can have that background field not be listed as a composition. It's just sort of, and it's only accounted for if the beam is not present in one place. Yes, and so the next we have the compositional initial conditions for these 4 compositional fields. So then what you do is you go into the initial composition model. We're actually going to describe all of these in terms of the function. And so then our variable names are X and Y. These describe the spatial coordinates. And then in this case, we did not need any function constants to describe it, although you could have added a constant which using these equations right here. Initially, the values of the stress tensor are 0. You could start with the pre-stressed model, but in this case, there's no reason to do that. And then what we're writing out here is the location of the beam in the model. So what we're saying is, inside the model, if the X value is less than 4.5 kilometers, if it's less than or equal to 4.5 kilometers, and if it's greater than a height of 2.5 kilometers and less than a height of 3 kilometers, the value of this compositional field representing the beam is going to be 1. If it's outside of that range, if it's outside of that rectangular domain we just described, then the value is going to be 0. And so then that basically is how you track materials. If the value inside aspect of this compositional field at a given point is 1, the material properties at that point are going to reflect it, are going to be completely composed of the beam, or they're going to be completely determined by the material properties of the beam. If the value of the compositional field is 0, it's going to be the values of the background, or the background low density, low viscosity material. And so then this is done through a volume fractions computation. And of course, then if the value of the compositional field the value of the compositional fields we're getting is between 1 and 0, then it's going to be some average between those values. So how about the element types in terms of sort of the elements we're using to describe temperature, composition, and Stokes? For composition and the Stokes, we're using the default values of 2, so then this is a quadratic element. For temperature, we're actually using a value of 1. We're using a lower order element. And the reason we did that is because temperature doesn't matter in this problem. It's temperature independent. And so then we can use a lower order element, which is less accurate to describe the temperature because it doesn't matter and it's just constant over time. The other feature of this model is you can actually use a discontinuous composition element, and in some cases a discontinuous temperature discretization, to more accurately track sharp interfaces over time. That's sort of a very rough approximation for that. Gary Puckett, one of the participants here, it was his postdoc and a number of other people who actually worked this out. And I apologize, I forgot to include the paper on this, but I can send an email around with a link to that paper. But basically what we're here is we're saying, this compositional element, this DG element, as is commonly known, it's going to be able to track the sharp interface between the beam and the surrounding material more accurately. And we also use that in combination with the limiter. And so for the stress values, we don't want to limit those stress values. And so what we're going to say is the maximum value of the stresses, it's 1E11 or negative 1E11. So values they're never going to reach. but we're going to say the maximum value of the beam is 1 and the minimum value of the beam is 0, which is going to prevent overshoots and undershoots. Newts. So in terms of the rheology and the governing equations, there is in the formulation subsection, if you're using viscoelasticity, you do need to set enable elasticity equals true. In the material model section, you would use in this case, we're using the viscoelastic material model. And then here's the values you need to prescribe. So we're assigning a density for all the fields. So then these first 3 are stresses. Then this is actually, did I include something I didn't need to there? Oh, I'm sorry, I apologize, yes. So then this right here is the background material. So the first value you list is the background material. So then it has a density of 2800, it has a viscosity of 1 × 10⁻18, an elastic shear modulus of 1E11. The next 3 values are for the stress tensor, or the viscoelastic stress tensor. And because of the way we ordered them in the code, and this is why we require very specific ordering when you enter these values in the compositional field, in the list of the compositional field names, these material properties actually don't matter and they're automatically excluded. So then these, the stress tensor components and things like if you're using plastic strain, for example, in later models, those are automatically excluded from the model, from the volume fraction computation. And so they don't actually affect the material properties within the model. They're not lithologies. They're just there to track a specific material. And then here's the value and then here's the beam. And so you have a density of 3,300. You have a 6 order of magnitude higher reference viscosity, and you have a 1 order of magnitude lower shear modulus. Here we're doing things,
Ask a question at this point.
Yeah.
Can you repeat and make a bit more clear why the properties for the stress fields are excluded from the material property calculation? Like, where is that happening, and why does Aspect know about this?
Yes. And so then we're excluding, I guess the first point is we're excluding these values because they're not a rock type. And so then this does actually not represent a volume of rock in the model itself. It just represents a property we're tracking to actually modify the properties of rocks. And so then the way these are excluded at each point within the material model is we'll actually check to see what compositional fields are present. So then, for example, we would check to say, okay, in this case, we'd look to say, what is the value of the beam right here? And if the value of the beam is 1, the model is going to say, okay, all of the thermodynamic and rheological properties, these are going to be set to the beam values because it has a value of 1. If, for example, the value of the compositional field here was 0.5 for the beam, then the material properties would be an average between the background material and the beam itself. If the value of the compositional field for the beam is 0, then the properties are going to be completely described by the background material. And of course, then if you have multiple lithologies, so then let's say I had 2 different beams with 2 different properties, that volume fraction computation average, or looking at what materials are present, would involve the background and 2 different beams. So it gets a little bit more complicated. But this is done automatically inside the material model. And so in this case, this would be actually a function the material model calls. And so then in the viscoelastic material model, we set it up so that depending on if you're using 2D or 3D, in 2D you have 3 components of the stress tensor, in 3D you would have 6 components. The ordering we use and the naming scheme we use automatically removes these from the volume fraction computation. And so then you don't have to worry about that. That's automatically taken care of. Renee, did that sort of answer the question?
Yes, I think so. So I think the most important part is this only happens in the viscoelastic and the viscoplastic material model. Is that correct? So if you had
Yes.
say a stress field and would use a different material model, then this stress field would be assigned some density or viscosity, and you would need to be careful about that. Is that correct?
Yes. Yeah.
Okay.
Yep, and and looking at that part of the code might be a good thing to go over in the discussion if people are interested in that. So then if we look then a little bit lower, then all of these terms right here, all these parameters are things associated with the viscoelastic computation in terms of calculating the effective viscoelastic viscosity and the stresses associated with it. And so then there's an option to use a viscoelastic time step, which is different than the numerical time step. And so then if you'll recall in the equations for the viscoelastic, viscosity, and the stresses, there was this delta and T is elastic. Then the best procedure to use is have that value be equal to the numerical time step. And that is the default. And so then here what we're saying is use a fixed viscoelastic time step, which would be different than the numerical time step. That option is not enabled, and we're setting it to false. If you do set this value to true, and then you have a deviation between this fixed elastic time step value you've prescribed and the numerical time step, then often it becomes advantageous to use an averaging scheme, which sort of, takes the difference between those two, or the stresses derived from those two time steps. However, in most cases, what I would do is keep these equal to false. I would just set these equal to false. This is the safest thing to do. And then the result of that is going to be that your elastic time step is always equal to the numerical time step. On the very first time step, on time step 0, we actually need to give the material model an elastic time step because it hasn't computed a time step yet. And so then this value, this fixed elastic time step, is always used on time step 0. And in this case, I've just set the value equal to the numerical time step we used. The last point is that in between different compositional fields, and so in this case, between the background and the beam itself, well, you need to do some averaging, right? And so then let's say the value is 0.5, or let's say the value of the beam compositional field is 0.5. That means you need to do an averaging, or the material properties are going to be some sort of average between the background and the beam. And there's different ways of doing that averaging. What we've done here is chosen an option called maximum composition, which means take the largest percentage of material, or I'm sorry, I'll back up. I'll say that again. I'll phrase that differently. It means that the compositional field with the maximum value, the material properties are going to be set equal to that. So then if the beam was, for example, 0.6, it doesn't matter that the value then of the background material is effectively equal to 0.4. The material properties of the beam, or the material properties of the model, are still going to be equal entirely to the beam at that point. So what we'll do in a minute is go back to the virtual machine, but what I wanted to first do is show you what it looks like after you run the beam for 50,000 years. You can then turn off gravity, restart the model after you've set the time to something like 250 or 500,000 years. And if you turn off gravity, then you've removed the driving force. And what is actually happening is the stresses which accumulate in the beam, they're going to provide a force which restores the beam to its original shape. And if you look at that in terms of the stresses, so then at 50,000 years, you had values of stresses on the order of 200 to negative 200 megapascals. Over time, these stresses are going to relax as they push the beam to its original shape. And then the stress values decrease over time. So what we can do now is, I think we have a few minutes to do this, is if you go back to the virtual machine, I'll switch the screen I'm sharing now. And at least on my end, the model has finished running. And so now what we can do is, if you want to open this model on your virtual machine, you can open pair view. You can either do it through, you can either go up to that screen and open it, as we did the last 2 days, or what you can do within the terminal is type pair view and then hit enter. Yes, and this should open pair view. And the nice advantage of opening pair view this way is it automatically puts you in the folder. It automatically sets your folder location to the current folder you opened it in. So then if we go to the output folder, sorry. Try that one more time. Oofda, sorry. Aye, aye, aye. Well, I'll give it a minute, but what you could do is basically you double click on output and then open solution.pvd from there. Sorry, I'm going to stop sharing quickly and see if that allows me to fix this. I may need to restart my virtual machine. I'm not sure what happened there with the mouse control. But what we could do during the break is we'll take a break in, let's say, 5 minutes, is what you could do is go into the model, or is open the parameter file again. You could change the end time of the model to 250,000 years. And to do this, you would say set end time equals 250 E3. Or then if you ran the model for 10,000 years, you could say just set the end time to 50,000 years. It just means your beam won't have undergone as much flexure, but then still the effects you'll see are still the same. And then after you've changed the end time, you can turn off gravity in the following manner. You would go to the gravity model subsection, and you would just say set magnitude equals 0. It was initially set to 10, but then if you set it to 0, then gravity is turned off. Because in this model we had set resume computation is equal to auto, what you can then do is, if you ran your model for 10,000 years or 50,000 years, all you have to do then is re-execute this command. So then if you just do MPI run, the shemp2, point to the aspect executable and the parameter file again, it'll automatically start off from from the point it left. And then this is sort of a really useful practice for other kinds of models. So then let's say you're modeling continental extension, but you want to say change the boundary conditions over time. Let's say you say after 10 million years, let's say plate motion change and you suddenly went to a compressional system. What you could do then is go into the velocity boundary conditions section and change your boundary conditions from tensional to compressional. And so then you can change basically, I think, almost any variable in the model after resume computation. But you can't do, I guess the one thing you can't do is you can't do things like remove compositional fields, or I don't think you can change the number of processors you're using to run the model. So when you resume the computation, you should always use the same number of processors. So I will go back and see if I can get back into my virtual machine. No, sorry. So maybe while I restart my virtual machine, this would be a good time to go over any questions before we go into the break.
I'll have a comment for you, John.
Yes.
You can actually change the number of processors. And
can you?
I believe that you can, and it's a useful feature if you want to switch to something that is more complicated. So you might want to have, let's say, fairly little mesh refinement in the beginning to get, let's say, to a steady state, and run this on a few processors. And then when you're there, you can add more mesh refinement and run with more processors after a restart.
Oh, that's fantastic. I didn't realize that.
Or if you have a more complicated material model, all of these sort of things are possible.
John, I think we have a question in chat. If users should rename the parameter file and the output files. because they are concerned they want to, if they can still compare the model results if they use the same parameter file and output directory. And if I understood you correctly, they should not change the parameter file and output file, because Aspect will restart from the endpoint of the previous model run and continue running. Is that correct?
Exactly, yes. And so then you can restart and it won't erase your old results. It'll just basically pick off from where it left off. So it's not going to remove the old output folder. It actually, well, even in the log.txt file you're using, it'll actually continue adding to that file itself, and it'll just keep adding it'll keep writing additional files to the solution folder as well. Alternatively,
but that is only the case in this model because you set the resume computation parameter to auto, right?
Exactly.
If that would be set to false, then it would start from the beginning and overwrite everything.
Yes, it would. And so another example, I can give another example of when it might be useful to copy the results, these results over to a new folder and then resume the computation in a different folder. So one example is I've been writing some models where I start out with the orthogonal continental extension and then I change the obliquity. So you go to obliquity of say like 15 degrees, 30 degrees, or 60 degrees. The starting point for those models with the varying obliquity is the same. It's the last endpoint of the orthogonal extension model. So what I do in that case is I'll create a bunch of new folders, copy the output folder to those new folders, and then the parameter file as well, and then restart the model with the varying obliquities. But because in that case, I want to run multiple models that started from the same initial model, then I copy things over to new folders. But in this case, though, I think in this case, it's probably advantageous to just run it in the same folder.
Okay, thank you.
Yep. It looks like there's a question from Gary. What output time do you suggest for the gravity equal to 0? Yep. Yeah, Gary. Yeah, I believe I just use the same output time every 10,000 years. You could change that to 100,000 years if you wanted to output less files, but it doesn't slow down the computation in any meaningful way. If that was the question. The end time I changed the model to was 250,000 years. And in fact, I will put this screen back up. Are there other questions before we take a short break? If not, then what has been the standard practice to take the first break is around 10 minutes, Renee?
Yes, I think that's the time we usually took so far.
Yep, so then let's meet at 10 minutes past the hour, and in India that would be 40 minutes past the hour. So thanks, and we'll see you in 10 minutes.